Hey guys, welcome back to another video. Um, I'm getting over a cold here, so if my voice sounds a little funky or if I cough a bunch, I apologize. Uh, so this is the first of two videos over Gibbs free energy, so delta G. So let's get this whole thing started here. Um, Most of what this is going to look at is these two questions. So how can we mathematically combine energy, so delta H, and entropy, so enthalpy and entropy, and then with that information, can we predict if something will be thermodynamically favored? Um, and we'll kind of define what that means as we go here too. So this is essentially what these notes are going to look at here. And so all of this comes from this man right here. So he's where we get Gibbs free energy. It's named after him. So 1873, he figured out a way to mathematically express a function that involved enthalpy and entropy, which are the two driving forces. And so from him, we get Gibbs free energy. So the spontaneity of a reaction involves both enthalpy and entropy, and is known as free energy. Okay, so this brings us to granddaddy equation for this. So you guys will see this equation a lot. You will use it a lot, so get really familiar with it. Delta G equals delta H minus T delta S. So delta G again is that free energy, so useful energy available from a reaction, is going to equal the enthalpy of that reaction minus temperature in Kelvin times entropy, so the chaos of the reaction. So if delta G is negative, that reaction is what we consider to be thermodynamically favorable in the forward direction. So going back really quick, if this delta G value is negative, then this entire reaction is what we call thermodynamically favored. If delta G is 0, then this thing is at equilibrium. It doesn't want to go forward or backwards in its current state. And then if delta G is positive, the forward reaction is not thermodynamically favorable, so you have to put work in order for this whole thing to happen. So up here, when we say thermodynamically favored, this negative delta G value, these are reactions that will move or proceed forward on their own without anything happening to them. So these are processes that if you just leave them alone and walk away, they will happen. Rust is an example of this. If you have metal and you leave it out in a humid environment, it has exposure to water vapor and oxygen, that metal will rust on its own. Now, it won't necessarily happen very quickly, but that process will happen in the forward direction without you or anything else causing it or forcing it to. So we also call this a spontaneous process. It's going to occur without external energy. So generally, we are talking about a system where delta H is less than 0, so negative, and delta S is greater than 0. And it, again, moves forward on its own. It can be sometimes quick, or sometimes it can be really long. Rusting will happen all on its own. So if you want to prevent rusting, you have to actively prevent it. So thermodynamically favored is when free energy of that reaction is higher, or sorry, free energy of the reactants is higher than free energy of the products, and so the entire thing will proceed spontaneously. That is not to say the same. So again, spontaneous in this case does not mean quickly. It just means without outside intervention. So down here you can kind of see that we will use the terms thermodynamically favorable. So in the book it says spontaneous. Know that we are talking about thermodynamically favorable, and AP prefers the phrase thermodynamically favorable. So get used to hearing that all the time. So there's this Bozeman video on this. It's worth watching. So if you want kind of some more background on this or just more information on this, feel free to watch this link here. But this is essentially what we're talking about here. So right here we have the reactant state, if you will, and you have product state. So this is thermodynamically favorable because given like enough incentive kind of on its own, this thing has lots of stored potential energy. So the second it can get any movement going, it will just roll straight down the hill all on its own. So the second it can get some of that potential to start turning into kinetic, this thing will just roll down the hill. So again, reactants, as they get opportunity to, they will slowly become products, and then you'll eventually hit this equilibrium point. So reactants are higher energy than products, or have higher free energy than the products do. So this should be thermodynamically favorable. It should be negative delta G. Okay, there's 4 different ways to solve these delta G problems. We're going to look at 3 of them in this video. So number 4, equilibrium, is what the next video is on. But we'll look at the first 3. So the very first one is molar free energy. And you'll see there it says product minus reactants. So you've seen something similar to this before. So this brings us to, hey, Big Mama equation version 3. Looks exactly like version 1 and 2. It's just now it has delta G instead of delta H or delta S. So free energy of the products minus the free energy of the reactants gives you delta G of the reaction. So this is the same. These are all standard values again. So one of the big things here is that just like delta H, standard values for elements in standard state is 0. So delta S is the only one where standard state elements are not going to be equal to 0. Delta G and delta H will both have a 0 value for elements in their standard state. Other thing is that this has standard conditions applied to it. So that means that we have to have conditions of 1 atmosphere, concentrations have to be 1 molar, and the values are all going to be at a temperature of 25 degrees Celsius. If we don't have this, this process does not work. So looking at this one, we have this reaction between nitrogen gas and hydrogen gas to make ammonia. Again, since these are elements in their natural state, then we now have 0 values. So because we have nitrogen gas, hey, we have a 0 value here. Hydrogen gas, 0 value here. So really the only value here is the product. So 2 moles of that product times negative 17 kilojoules per mole minus the reactants, well, that's, 1 times 0 plus 3 times 0, so it's nothing. So it gives us negative 34 kilojoules. So this thing is thermodynamically favorable. So yes to it being thermodynamically favorable. Okay, another problem. Again, we still have 1 element in its standard state, so this guy's a 0. Everything else has values of kilojoules per mole. So products, so 1 mole of carbon dioxide times its value plus 2 moles of water vapor times its value minus 1 mole of methane plus, well, here's oxygen times 0, so this is going to not do anything. gives us the value of the product side, gives us value of the reactant side. So this entire thing has a free energy value of negative 801 kilojoules. Again, it's a negative value, so hey, yeah, totally thermodynamically favorable. This is a combustion reaction, if you notice here. So yeah, like methane likes to burn, and it will do so, given the incentive to do so. Okay, so again, this products minus reactants thing only works if we are talking about conditions at 25 degrees Celsius. Delta G is very temperature dependent. If we were to go back and look at that granddaddy equation, so try and get back in here. Notice this whole T value right here. If we're not at a specific temperature, this value changes. So we can only use the standard values if we're dealing with things at standard conditions. So trying to get back to that slide here really quickly. So again, products minus reactants, only for things at 25 degrees Celsius. If we're not at that, then there's other ways to solve this. So if we're at standard values, products minus reactants. Otherwise, just use the granddaddy equation, and that's what you guys will use most of the time here. So that brings us to, hey, granddaddy equation right there. So here's this problem right here. We have water that is boiling. So if we're trying to get this water to boil, well, water is going to boil when delta G equals 0, because that's when there's going to be an equilibrium between these two. So if we set the granddaddy equation equal to 0, we can plug in delta H minus T delta S. We can use that to solve for this temperature value to figure out what the thermodynamic boiling point is. And that's going to be about 370 degrees Kelvin, or 97.37 degrees Celsius. Okay, so this one's a bit more involved. So here, it still wants us to solve for delta G. It also wants us to calculate delta H and delta S. So essentially, we have to use these values to find delta H for the reaction, these values to find delta S of the reaction, and then all of that to find delta G. If you notice here, we have formation values. So heat of formation, standard delta S. So products minus reactants, and then we can use that to solve for delta G. So products of minus reactants for delta H gives us delta H for this reaction of negative 198. Products minus reactants for delta S gives us negative 223 joules per degree Kelvin. But if we have kilojoules here, we also need kilojoules in this value. So we have to convert that and then plug it in. So when we are using when we're solving for delta G, delta H has to be in kilojoules, or will probably always be in kilojoules. And if this is in kilojoules, guess what? This has to be in too. Delta S is very commonly in joules per degree Kelvin. If we look back here, the values it gave us were kilojoules per mole and joules per K per mole. So this is very common, so make sure you keep an eye on this. Because delta S is commonly in joules, whereas delta H is kilojoules. Okay. So another problem. This one just wants us to predict. So we're not actually solving anything out here. So assuming no change for delta H and delta S, what happens to delta G when we increase the temperature? So if we have this system, do we predict that delta G will go up, or do we predict that delta G will be a more positive value or a more negative value if we increase the temperature? So looking at this, like, take a second, see if you can't figure it out, maybe pause the video, and then here's how you solve this one. So we can assume that delta S for this system is going to be a negative value. We can assume that because we have 4 moles of gas here going to 2 moles of gas here. So this system is going from chaotic to more organized, which means that the change in entropy is going to be negative. So if that's true, then looking at this delta G equation, we have delta H here. We have a large T value because we're increasing the temperature here times a negative value. So we have essentially a negative, or we have this subtraction. So we're going to be, as the temperature increases, we're going to be subtracting an increasingly larger negative value over here. So essentially this becomes a much larger plus sign. So as temperature increases, delta G is going to become more positive or less thermodynamically favorable. And it will eventually hit a point where this side of the equation is larger than this part, which means that delta G will straight up equal a positive value if it doesn't already. And it will be completely not thermodynamically favored. Okay, third way of solving this is Hess's law. So we can bring back Hess's law. So this is going to work the same as enthalpy. So sum up equations using the exact same guidelines as enthalpy. Here's the only thing that's different. So we still have one reaction, we still have a second reaction, and instead of having delta H values, hey, we have delta G values now. Same thing, I'm trying to get them to equal this equation, so if graphite's on this side, I need to flip this reaction. Gets me graphite on the product side. O2 is going to cancel out. CO2 will cancel out. So you end up with diamonds going to graphite. Forward reaction. As we solve this thing out, hey look, delta G equals negative 3 kilojoules. Which means that diamonds, given enough time, will on their own become graphite. Now, this thing is very numerically close to 0, so it's not massively thermodynamically favorable. And again, that doesn't say how fast it is. So just because it's spontaneous doesn't mean that this will happen instantly. This could take an extremely long amount of time. So your diamonds are fine. They're not going anywhere for a very long time. Just eventually, they'll all be graphite. So putting it all together. Delta G if positive, not thermodynamically favored. If it's negative, yes. So if delta H is negative and delta S is positive, then this thing will always be thermodynamically favored. So negative here, positive here, yes. If they're both positive, then it's favorable at high temperatures. If they are both negative, then favorable at low temperatures. If you have a positive here and a negative here, will never, ever, ever be favorable. So kind of a different way of looking at that. So if we have y-axis is delta S, x-axis is delta H. This quadrant right here will have a negative value here, a positive value here. So delta G will equal a negative value minus a positive value. So this thing will always end up solving a negative delta G. If we go to this quadrant here, they're both positives. So positive here minus a positive times this temperature value. So the second this value is larger than this value, delta G will be negative. So at higher temperatures, this side of the reaction is going to, or this side of the equation is a larger value than this side. Over here, same idea, except for now we have negatives. So negative minus a negative temperature. So we want to try to keep this a low temperature value because we want to maintain this negative. This side right here has, if temperature grows too much, this side becomes too large. Minus a negative becomes positive, so this guy's positive. Okay, excuse me, tickle my throat. And then, last but not least, over here, positive minus a negative, this thing will always be positive. Okay, so if delta H is negative, delta S is positive always. If delta H is positive and delta S is negative, never. Both positive at high temperatures, both negative low temperatures. Okay, so this one is interpreting the graph. So we have this delta H line and then this T delta S line. So we're talking about, and you can see where 0 is. So this line is positive, like we have a positive value from here up, we have a positive value from here. So delta H is positive, T delta S is positive from this point over. So that means that over here, where this value is low, we end up with a positive delta G. From here on over, this value becomes larger than this one, so we have a positive minus a much larger positive, so delta G is negative. So this particular reaction, whatever temperature this is right here, if it's less than this temperature, is not thermodynamically favored. If it's greater than this temperature, it is thermodynamically favored. So we have this kind of cutoff point right here. So here it is thermodynamically favored, here it's not. So this is one of those, this is that upper right-hand quadrant again. And then the last thing to finish off these notes is just a quick little quote by Havel here. So just as the constant increase of entropy is the basic law of the universe, so it is the basic law of life to be ever more highly structured and to struggle against entropy. So hope that finishes you guys off, and we'll see you for the last part of these delta G notes.